Welcome to the 32nd lecture on computational mathematics with SageMath. In the last lecture, we looked at how to define vector spaces in SageMath and work with various concepts like linear span, coordinates of a vector, finding basis of linear span and things like that. Let us look at some more examples of vector spaces and some other concepts in this lecture. Okay. So, let us look at, suppose we want to work with a set of all polynomials of degree less than equal to 3. This is P3R is set of all polynomials of degree less than equal to 3 over R. So, this is a vector space over R, and suppose let us say we define 4 vectors in this. F1 is equal to 1 plus x, F2 is equal to F1 is 1 plus x, F2 is 1 minus x, F3 is 1 minus x cube, and F4 is 1 minus x to the power 3, and we want to check whether this is a basis. If so, we can find coordinate of any vector in this, that means any third degree polynomial with respect to this basis. So, let us just check. How do I check whether this is a basis or not? So, first of all, we need to show that this is linearly independent, and I am sure all of you know that this is a vector space of dimension 4. So, any 4 vectors which are linearly independent will form a basis. So, how do I check whether this is a linearly independent? So, if I take A1 times F1 plus A2 times F2 plus A3 times F3 plus A4 times F4, if this is equal to 0 and we can get A1 equal to 0, A2 equal to 0, A3 equal to 0, A4 equal to 0, then we will prove that this F1, F2, F3, F4 are linearly independent. So, let us find out what is A1 times F1 plus A2 times F2 plus A3 times F3 plus A4 times F4, and let us expand that expression, and when we say collect P dot collect, so I think this we have not run. If when we say P dot collect, it will we need to declare A1, A2, A3, A4 as variables. So, let us say VAR in the bracket A1, A2, A3, A4, right. So, when you say collect these coefficients, these coefficients are corrected. Now, what you have is this is equal to 0. 0 means 0 polynomial in degree 3. So, the first term, the coefficient of x3 should be x to the power 3 should be 0. That means A4 is 0. Similarly, since A4 is 0, the coefficient of x square is this. So, when A4 is 0, then at A3 is 0. So, A3 and A4 are also 0, and from this coefficient of x, A3 and A4 are 0. Therefore, A1 minus A2 is 0, which is same as saying A1 is equal to A2, and now the constant term which is also 0, which is A1 plus A2 plus A3 plus A4 is equal to 0. That would mean since A3 and A4 are already 0, A1 plus A2 is equal to 0, and but A1 is already equal to A2. This is same as saying 2A1 is 0, and hence A2 is 0. So, this shows that this set of vectors are linearly independent. However, you can do this checking using inbuilt function solve. So, how do you do that? You collect the coefficient of x cube and equate it to 0, coefficient of x square equated to 0, coefficient of x equate to 0, and when you say P of x equal to 0, that is a constant term, that is also equal to 0, and solve this for A1, A2, A3, A4, you should get this as 0, 0, 0, 0 solution, right. So, that is how you can check whether set of polynomials in P3R is a basis is linearly independent or not. So, it took a little while and we get this is linearly independent, and hence this forms a basis. Now, suppose I have a vector which is 2 plus 3x minus 4x square plus x cube, and we want to find coordinate of this vector. This with respect to the given basis F1, F2, F3, F4. So, how do I do that? If coordinates are, let us say A1, A2, A3, A4, that means we should have A1 times F1 plus A2 times F2 plus F3 times F3 plus A4 times F4. This should be equal to 0. So, that is same as saying you just simply we have already defined P as summation ai fi. So, you collect the coefficients of this summation ai fi and equate it to the coefficient of f. That is what we are doing. So, coefficient of P xq coefficient of P equated to xq coefficient of f, x square coefficient of coefficient in P equated to the x square coefficient in f, and so on. And when you do that, you will get the solution. So, A1 is 1, A2 is 3, A3 is -1, A4 is -4. So, if you try to, for example, check what is F1 plus 3 times F2 plus -1 times F3 -1 times F4, this should be equal to F, right. So, we have found the coordinates of this polynomial with respect to this basis. So, that is very simple exercise. Now, let us look at you must have studied what is called dimension formula. So, if you have two vector subspaces, let us say W1 and W2 of V, you can generate more subspaces. One of them is W1 intersection W2 is a subspace of V. Similarly, W1 plus W2 is also a subspace of V, and dimension of W1 plus W2 is related to dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. So, let us verify this dimension formula, and showing this is actually a standard theorem in linear algebra. I am sure you must have seen this. Okay. So, let us start with V to be q to the power 5, q to the power 5, and let us take two sets B1 and B2 of having 4 elements, 4 random elements in this. So, it is possible that B1 generates 4 dimensional subspace of V, B2 also generates 4 dimensional subspace of V. So, let us define this, and let us define W1 to be the linear span of B1, that is a vector subspace of dimension 4, W2 also a subspace of V generated by B2, that is also a subspace of dimension 4. So, dimension of W1 and dimension of W2 are 4 each, and let us find out what is intersection. So, the intersection is of W1 and W2 can be obtained using this intersection function. So, W1 dot intersection W2 gives you intersection of this. So, if you want, I'll call this as let me call this as U, that is the intersection. So, if I say what is U, this gives me vector space of dimension 3. The intersection is vector space of dimension 3. And what is W1 plus W2? W1 plus W2 can be obtained by just W1 plus W2, and this is actually a vector space of dimension 5. So, this is entire space in fact. And then let us verify the dimension formula. So, dimension of W1 plus dimension of W2 minus W1 dimension of W1 intersection W2, is it equal to dimension of W1 plus W2? The answer should be true. So, this is verification of dimension formula. Of course, you can ask how this W1 plus W2 generated, how is this W1 intersection W2 generated, right. So, I will leave that as an exercise. Just take some example and take some W1 and W2 subspaces which could be linear span of some vectors, and see how you can generate W1 plus W2 and W1 intersection W2, right. Next example, let us look at finding a basis of linear span for a finite set. Okay. This actually we have already seen, but let us look at it again. Suppose I have q to the power 4 and I have 6 vectors V1, V2, V1, V3 up to V6, and S is the set containing V1, V2, V3, V4, V5, V6. And if I want to find the basis for this, what we can do is we can take a linear, of course we can take linear span of this and find the basis using inbuilt function. However, if you want to do manually, what you can do is you can look at these vectors and form a matrix, column matrix whose first column is V1, second column V2, and so on, and then apply RR EF. When you apply RR EF, you can see here this column, this column, this column, first three columns, they form actually identity matrix. So in fact, actually we are generating this as a row matrix, where rows are vectors in S. First row is V1, second row is V2, and so on, and then apply RREF. This will give you the basis, and which is same as what you got using inbuilt function. So in order to find basis of a vector space LS, you simply take vectors in rows and apply RREF. This we have already seen. However, you can also do it with column matrix. So when you do the RREF over column matrix, then you can find the pivots of this. So pivots in this case, pivot of this column matrix. So this is 0, 3, 4. 0 means first column, 3 means fourth column, and this is fifth column. So first column, that corresponds to V1. This is the fourth column, corresponds to V4, and this is the fifth column, which is V5. So that in this case, that means basis for this is going to be V1, V4 and V5. Those are the linearly independent vectors, and every other vectors are linearly dependent on these three. In fact, you can try to check each of these pivot, I running over this pivot, and Si over I, these are the three vectors which are linearly independent, and it forms a basis for LS, right. You can apply RREF to M, and then you will see that first column, fourth column and fifth column forms an identity matrix. So these are the pivots. Pivots are 1, second column is twice first column, so that's not. Third column is also minus 1 times the first column. So third column, fourth column is linearly independent with the first column. So first column, fourth column, and this fifth column, they form a basis. The last column is actually linear combination of first and third, sum of first, not first and third, first and fourth, right. Let us look at another example. This is again very for example, this problem, this you must have seen the theorem that any linearly independent set can be extended to a basis. By the way, this previous problem which we saw is what? It is actually if you are given a set of vectors in a vector space V, then from that you are able to generate a basis for the linear span. That is what you see. Now we are looking at, you start with a linearly independent set that can be completed to a basis of the vector space. Of course, we are talking about everything in finite dimensional. So let us say V is equal to Qq to the power 4, U1, U2, U3 are these three vectors, and let us check whether they are linearly independent. Yes, they are linearly independent. So you want to extend this to a basis of Q5. So how do I do that? Generally in the theorem, what you would have seen is that you take linear span of this U1, U2, U3 and take a vector U4 which is outside this linear span. Now how do you want to select something which is outside this in some arbitrary space is not not very convenient way of selecting, right. So and then after that, once you have selected U4 which is not in the linear span of U1, U2, U3, U4, you can show that U1 to U4 will be linearly independent. So again you take a linear span. In case it is not the complete fold vector, then you select something which is outside linear span of U1, U2, U3, U4. So you keep on continuing this. That is what the proof of the theorem. So in this case, what we can do is, we can look at these vectors U1, U2, U3, U3 and look at this standard basis U1, U2, U3, U4, U5. So if U1 is in the linear span of U1, U2, U3, there is no problem. You can take E2. If E2 is also in linear span, don't leave it. So you keep on checking. Not every U1, U2, E3, E4, E5 will be in the linear span. Otherwise, this whole thing will span the entire V, which is not correct. So therefore, the U4 will come from one of these EI. Similarly, U5 will also come from one of these EI. So we can take this as a clue, and what we can do is we can augment take this column matrix U1, U2, U3 and augment identity matrix to this matrix. That is same as saying you are augmenting E1, E2, E3, E4, E5. Let us look at what is this M. Right. So M, the first column is U1, second column U2, third column U3. This is E1, E2, E3, E4. And now find pivots of this. Right. You can find RREF, that will also give you pivots. So pivots are first 3 columns here, and then this is not the case. This is the one. So this corresponds to E1. This corresponds to E2. This is also not there. This is E4. So the pivots are 1, 2, 3. 4 is not there, 5 and 7. So these are the pivots, and therefore what will be the basis? Basis will be U1, U2, U3, and then E2, and then E4, because this is E1, E2, E3, E4. So U1 to U3, and then U2 and E4. That's what you have. You can just find the pivots. So the pivots are 0, 1, 2, 3 and 4 and 6. So that corresponds to U1, U2, U3, E2 and E4. That's a basis which is obtained by completing this linearly independent set of vectors to a basis. Right. Another thing which you can see, suppose you are given 2 bases and take any vector, you can find coordinate with respect to one basis, coordinate with respect to another basis, and how are these coordinates related to this basis B1 and B2. Let us say B1 and B2 are 2 bases of vector space V. That is what we want to look at. So if you have, let us say, 2 bases B and another basis, let us say C. B is V1 to Vn, C is W1 to Wn. These are the 2 bases, and suppose I have a vector small v which is whose coordinates are A1 to An. These are the coordinates. So V is summation Ai Vi, that means Ai's are coordinates. So that we can write as a column vector, coordinate vector. And similarly with respect to the basis C, I have this coordinates, let us say V underscore C, and then one can show that this the coordinate of V with respect to beta and coordinate of V with respect to, let us say, C, they are related by a matrix which we let me denote this by M underscore B C, that is called a change of basis matrix or transition matrix. So this is V C is multiple of a matrix multiplication with this. Now how does one obtain this matrix? So that is quite actually easy, and so what one can do is this matrix will be a matrix whose first column will be nothing but coordinate of V1 with respect to the basis C. Coordinate of the second column will be coordinate of V2 with respect to basis C, and so on. Coordinate of Vn with respect to C. That is what you need to do. And V1, V2, Vn are what? They are the elements of the basis B. So let us look at this an example. So let us say beta is this 4 vectors in Q4. This you can check, this forms a basis. Similarly, let us say C, these are again some 4 vectors, it forms a basis. We want to find this transition matrix. So how do we do that? In order to do this, let us declare V as Q4, V1, V2, V3, V4 is this, capital B is this set, and let us generate a subspace with this B as a basis, that is W1, and I have a vector V which is 3, 2, 3, 2. That we want to find coordinate of V with respect to this beta B. So that we can obtain, let me call this as V underscore B, and that is the column matrix with these coordinates. So let us see here. So that's the column the coordinate vector of V with respect to the basis capital B. Okay. Similarly, let us find basis of same vector V with respect to basis C, which is W1, W2, W3, W4. These are W1 to W4, and exactly the same way let us find the coordinate. So these two are this is coordinate of V with respect to basis beta, this is coordinate of V with respect to coordinate C, and with respect to basis C, and let us see how they are related. So as I said, how they are related, so that is a column matrix whose first column is coordinate of V1 with respect to basis C. So that means you how do I find that? We have already seen that can be obtained by using RREF. So that is what we will look at, but first let us take the coordinate of BI with respect to basis C. So that means you are finding coordinate of BI with respect to subspace W2 which has basis C, and then take all these vectors, write this as column matrix. So that is your matrix, transition matrix or change of coordinate matrix. This is what you get. Now the same thing you can do it with by augmenting let us say the matrix inside VB, you augment this this CC. So what we are doing in this case, you are finding the coordinate of each vector in C with respect to basis B. That is what you are doing. Similarly, if you take if you augment BB over CC, that means you are augmenting the V1 to the set the matrix whose first 4 columns are coming from basis C, and then apply RREF. Then the last 4 columns will be nothing but this matrix which you have obtained. So that is your MCB, right. So this you can use RREF or you can use inbuilt function. Now let us check the coordinate of V with respect to C. Is it equal to the matrix and this transition matrix MBC times coordinate of V with respect to capital B, and the answer is true. So we have verified this result that the coordinate of V with respect to 2 bases are related to this change of matrix change of basis, that is called transition matrix. And of course you could also see what is VB will be equal to this inverse times VC. So that you can check. So in fact you can just verify. So first you can find the coordinate of C with respect to the basis B, and let us call that matrix at MCB, and then MCB and MBC, they are inverse of each other. They are inverse of each other. So if I take the multiple of these two, it should get identity matrix, right. So that is how they are related. Now let us look at one last topic. Suppose you want to define a vector space over finite field. So let us take an example. Suppose I have a vector space defined over FP3 of dimension 4. So that is capital B, capital V, and so we can ask for what is dimension of this, it will be 4, and you can even find out in this case what is the cardinality. So any vector will have 4 components, and these 4 components will come from these elements in GF3, which will take value 0, 1, 2 or 3. So the cardinality should be 3 to the power 4, which is 81. Similarly, you can find basis of this. So basis in this case will give you the standard basis 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1, right. Now suppose I have 3 vectors, some arbitrary 3 vectors V1, V2, V3, V4, and we can check this is how we can define a vector in capital V. Capital V, in the bracket you write in the round bracket you give the components in square bracket, and you can check whether V1 lies in capital V, whether V2 lies in capital V, and the answer should be. So that is how you can define vectors in this space. Now for example, you can ask for subspace spanned by V1, V2, V3. So again exactly the same way, this is a 3-dimensional subspace spanned by this. So for example, in this case let me let me change V3. I will make this as twice. So this is 2, this is 2, 4 would mean 1, this would be 0. So if I say this and then find linear combination, you can see it, now it is a subspace of dimension 2 of this. Similarly, you can work with matrix space and try to find its basis, dimension, etc. Right. So let me leave you with these simple practice exercises. First exercise is actually to verify this dimension formula, which we have already done. We did it in, I think, Q5. Now I am asking you to do it in Q4. Right. Now you can write a basis of P3R whose every element is of degree 3, and then find coordinate of 1 plus x square plus x cube with respect to that basis. The next problem is find a vector space V of 2 cross 2 matrices over GF5. So the again matrix space will be used. You can find the cardinality of this set, that is how many elements are there. You can also find cardinality of set of all 2 cross 2 non-singular matrices. These are called GLN2. The next, define two bases B1 and B2 of Q4. Find coordinate of, let us say, this vector with respect to each of these, and find the transition matrix and then see how they are related. And the last question is find a basis of L of this. So that's again quite easy. So these are very simple exercises. Okay, so next time we will look at the concepts like linear transformations and things like that. Thank you very much.